Good morning, everyone. Welcome to Foundation Physics Lecture 5 on energy and momentum. These aren't just abstract ideas. They are essential for understanding how the world around us works, from a ball rolling down a hill to the safety features in a car. Moving to slide 2, let's quickly look at what we'll cover today. We have quite a packed agenda, but each topic builds upon the last. First, we'll start with Hooke's law, which describes the behavior of springs. Then, we'll explore the basic energy model and energy diagrams, understanding how energy transforms. Next, we'll differentiate between conservative and non-conservative systems. Following that, a brief look at power. Then, we'll move to momentum and the principle of conservation of momentum. And finally, we'll end with the concept of impulse and its real-world applications. Let's begin. Starting with Hooke's law on slide 3. On slide 4, you can see a visual representation of Hooke's law. Robert Hooke, a brilliant English scientist, observed that when you stretch or compress a spring, the force required to do so is directly proportional to the amount of stretch or compression. Imagine you have a spring with a natural, unstretched length, which we call L0. When you hang a mass from it, the spring stretches to a new length, L. The displacement, delta S, is simply the difference between the new length and the original length. Delta S equals L minus L0. At equilibrium, meaning the mass is not moving, the upward restoring force from the spring, FSP, perfectly balances the downward gravitational force, Fg, which is mg. So FSP equals Fg equals mg. Moving to the next slide, slide 5, we see a graph that beautifully illustrates Hooke's law. It shows measured data for the restoring force of a real spring. As the displacement, delta S, increases, the restoring force, FSP, also increases in a linear fashion. This linear relationship is key. It tells us that FSP is directly proportional to delta S. The constant of proportionality, which is the slope of this line, is called the spring constant, denoted by K. The units of K are newtons per meter, or N per m. So we can write the magnitude of the spring force as FSP equals K delta S. Now on slide 6, we refine our understanding of Hooke's law. The spring's restoring force always acts in the opposite direction to the displacement. If you pull the spring down, the force pulls it up. If you push it up, the force pushes it down. Therefore, when considering the component of the spring force in the direction of displacement, we add a negative sign. FSP sub S equals negative K delta S. This negative sign signifies that it's a restoring force. So what's so special about Hooke's law? What does it imply? Well, as we've seen, the restoring force is directly proportional to the spring's displacement. Furthermore, the area under this force displacement graph represents energy. This is the energy stored in the spring when it's stretched or compressed. We call this elastic potential energy, U sub S. So let's now return to this form of energy. Let's delve deeper into elastic potential energy, shown on slide 7. If we consider the average restoring force, F, when stretching a spring from rest, delta S equals 0, to a distance S, it's the average of the initial force, 0, and the final force, Ks, so F is equal to Ks plus 0 divided by 2. The work done, W, in stretching or compressing a spring from rest to a distance S is given by work equals force times distance. Using the average force, this becomes work equals Fs equals Ks over 2 times S equals 1/2 Ks squared. This work done is now stored in the spring as elastic potential energy, U sub S equals 1/2 K delta S squared. On slide 8, we see another example of elastic potential energy at play, a slingshot. When you pull back the elastic band, you store elastic potential energy. Release it, and that stored energy transforms into kinetic energy of the projectile. This idea of energy transformation is central in physics. We are often interested in how energy changes from one form to another. To analyze this, we must briefly look at the basic energy model in physics. But before that, we must acknowledge one other important form of energy. Before that, let's briefly touch on thermal energy, shown on slide 9. Thermal energy, denoted as ETH, is essentially the sum of the microscopic kinetic and potential energies of all the atoms and bonds that make up an object. Think of it as the internal jiggling and vibrating of particles. This energy often arises as a result of friction. Sometimes friction is useful, like when you use brakes on a bicycle. Other times it's not so useful, like when it causes wear and tear in machinery. But in all cases, friction generates thermal energy. Transitioning to the next major section, on slide 10 we have the basic energy model. On slide 11 you'll find a diagram of this model. It shows a system interacting with its environment. Energy can come into the system, be transformed within the system between kinetic, K, and potential, U, and also into thermal energy, ETH, or go out of the system. A crucial concept related to energy transformation is the law of conservation of energy. Within an isolated system, the total energy remains constant, although it can change forms. If we simplify things and assume no energy is lost due to thermal effects, meaning no friction, then we're looking at the law of conservation of mechanical energy. This concept is further illustrated with a spring ball system on slide 12. If we ignore friction and gravitational potential energy for a horizontal spring, or assume the height doesn't change significantly, the total mechanical energy is conserved. The equation Kf plus UgF equals Ki plus Ugi represents the conservation of mechanical energy, where K is kinetic energy and Ug is gravitational potential energy. For our spring system, where elastic potential energy is involved, this equation transforms. We replace Ug with Us, giving us 1/2 mvf squared plus 1/2 k delta s squared equals 1/2 mvi squared plus 1/2 k delta si squared. This means the initial sum of kinetic and elastic potential energy equals the final sum. On slide 13, the equation for an object moving without friction on an ideal spring obeys Kf plus Usf equals Ki plus Usi, where Us equals 1/2 k delta s squared, as we just discussed. On slide 14, we observe an important characteristic. Because delta S is squared in the elastic potential energy formula, Us is always positive, whether the spring is stretched or compressed. This means storing energy in a spring always requires work regardless of the direction of displacement. To visualize these energy changes, we use energy diagrams or bar charts. They help us understand how different forms of energy convert into one another during motion. Let's visualize this with energy diagrams as seen on slide 15. Here's an energy diagram for a mass on a horizontal spring. The blue curve represents the potential energy, which is a parabola because of the delta S squared term. The horizontal line represents the total energy of the system. You can set this total energy to any height you wish simply by how much you stretch or compress the spring at the beginning of the motion. The further you pull or push the spring, the more total energy you add to the system. On the next slide, slide 16, we refine our understanding of the elastic potential energy given by the parabola. Us equals 1/2 k times x minus xe squared. Here, x is the current position and xe is the equilibrium position. So x minus xe is our delta S. The shape of this parabola, specifically how narrow or wide it is determined by the spring constant, K. A stiff spring will have a large K, resulting in a steeper, narrower parabola, meaning more energy stored for a given displacement. A soft spring will have a small k, a wider parabola, and store less energy for the same displacement. This constant k is unique for each material. Now, on slide 17, we see the initial state of this system. The mass is released from rest at an extended position x equals xr. At this point, its velocity is 0. V sub x equals 0. So its kinetic energy, k, is also 0. All the total energy, Te, is in the form of potential energy, Ue. As the mass moves, Ue converts to k and back again. It's extremely important to remember the key assumption we're making here. No energy is lost due to friction. In other words, mechanical energy is conserved. If friction were present, some of that mechanical energy would convert into thermal. Let's transition to conservative and non-conservative systems, the topic of slide 18. On slide 19, we define what a conservative system is. A conservative system is one where the total mechanical energy, that's kinetic and potential energy, remains constant, assuming other forces like friction are negligible. Think of an ideal pendulum swinging back and forth. If there's no air resistance, it would swing forever, converting gravitational potential energy to kinetic energy and back again. The forces that act to conserve this mechanical energy are called conservative forces. Examples include electric force, gravitational force, and elastic force from springs. Moving to slide 20, a key characteristic of conservative forces is path independence. A conservative force has an associated potential energy. The most defining characteristic is that the work done by a conservative force moving a particle from point A to point B is independent of the path followed. Look at the diagram. Whether the particle takes path 1 or path 2 from A to B, the work done by the conservative force, F, in this case gravity, which causes a change in potential energy, delta U equals mgh, is the same. The work done by a conservative force, Wc, is equal to the negative change in potential energy. Wc equals negative delta U. So, if a force, like gravity, does work, minus mgh, then the change in potential energy is mgh. On slide 21, we introduce non-conservative forces. These are forces for which the work done does depend on the path taken. The most common example is friction. Other non-conservative forces include applied forces, like a push or pull, and tension, unless they are acting in a very specific, path-independent way. The friction force, F friction, always does negative work on moving objects, converting mechanical energy into thermal energy. The work done by friction, W friction, equals negative mu sub k times m times g times the change in S. Directly depends on the distance over which it acts, delta S. This means the longer the path, the more work friction does, and the more mechanical energy is lost. For our pendulum example, air resistance is a non-conservative force. It causes the pendulum to slow down and eventually stop. It doesn't conserve the mechanical energy of the system. Instead, it converts it into thermal energy, making the air and the pendulum slightly warmer. Slide 22 further explains how non-conservative forces, like kinetic friction, work. When two objects slide against each other, their atomic interactions at the boundary cause friction. This process transforms the macroscopic kinetic energy of the moving objects, K macro, into thermal energy, ETH, in both objects. This is why things heat up when they rub together. This kinetic friction is a type of non-conservative force, and it's sometimes called a dissipative force because it dissipates or spreads out mechanical energy as thermal energy. As shown on slide 23, dissipative forces always increase the thermal energy of a system. They never decrease it. You can't cool something down by rubbing it. The increase in thermal energy is equal to the work done by friction. Delta ETH equals Fk times delta S. Now that we've explored energy and forces, let's shift our focus to the rate at which work is transferred or energy is transformed. This rate is called power. Now, for our next section, on slide 24, we focus on power. On slide 25, you see a cyclist, a great illustration for power. Power is a measure of how quickly work is done, or how quickly energy is transferred. Mathematically, power, P, is defined as the rate at which work, W, is transferred over time, T. P equals dW dt. This is the instantaneous power. If an object is moving with a velocity vector v and a force vector F is acting on it, the power delivered to the object by that force can also be expressed as the dot product of the force and velocity vectors. P equals F dot v equals Fv cosine theta. Here, theta is the angle between the force and velocity vectors. This means power is maximized when the force is in the same direction as the velocity. Think about a cyclist working hard to push the pedals in the direction of motion to go faster. The SI unit for power is the watt, named after James Watt, who improved the steam engine. 1 watt, 1 W, is equal to 1 joule per second, 1 J per second. Let's move on to our fifth major topic, momentum and conservation of momentum, found on slide 26. On slide 27, we start with the historical context of momentum. Momentum as a concept was introduced by the French philosopher and scientist René Descartes even before Newton. He considered it the quantity of motion. Let's look at his idea with this example. Imagine a 5-kilogram ball moving at 10 meters per second. Now compare that to a 45-kilogram ball that is motionless. What happens if the 5-kilogram ball collides with the 45-kilogram ball? And what if a much heavier 50-kilogram ball is moving at a much slower speed of 1 meter per second? However, as we see on slide 28, Descartes' initial definition of momentum was simply mass times speed. This had a problem. Consider two objects of equal mass moving directly towards each other with equal but opposite speeds. According to Descartes' definition of momentum, their total quantity of motion might seem to add up, but when they collide, they come to a complete stop. Where did the quantity of motion go? This is where Christian Huygens, another brilliant scientist, made a crucial correction. Momentum needed to be a vector quantity, not just a scalar speed. He replaced speed with velocity. So, the proper definition of momentum, denoted by P, is P equals mass times velocity. Because velocity is a vector, momentum is also a vector, meaning it has both magnitude and direction. This solves Huygens' problem, as the momenta of the two colliding objects would be equal and opposite, summing to 0. Now, how does momentum relate to force? Slide 29 explains. Sir Isaac Newton, the famous English physicist, originally stated his second law of motion not in the form F equals ma that we often learn first, but in terms of momentum. He called mv the quantity of motion. Newton's second law, translated into modern language, essentially states that a force is required to change the momentum of an object. This means if you want to increase its momentum, decrease it, or even change its direction, you need to apply a force. More formally, as presented on slide 30, Newton's statement of the second law is the rate of change of momentum of an object is equal to the net force applied to it. This is expressed by the equation sigma F equals dp dt. Here, sigma F, the capital Greek letter sigma means sum of, represents the net force applied to the object, that is, the vector sum of all the forces acting on it. On slide 31, we can easily derive the more familiar form of Newton's second law, sigma F equals ma, from this momentum-based equation.
if we assume mass is constant. If P equals mv, then differentiating with respect to time gives sigma F equals dp dt equals d of mv dt. If mass m is constant, we can pull it out of the derivative. Sigma F equals m times dv dt. Since dv dt is the acceleration a, we get sigma F equals ma. This shows that the F equals ma form is a special case for constant mass. One of the most powerful consequences of Newton's laws is the law of conservation of momentum. It's essentially a reworking of Newton's laws applied to systems. This slide shows a common example, a collision between two billiard balls. The law of conservation of momentum, along with conservation of energy, is fundamental for analyzing collisions and other interactions between objects. On slide 33, let's consider an interaction between two objects, A and B. From Newton's third law, we know that the force A exerts on B, Fa on B, is equal in magnitude and opposite in direction to the force B exerts on A, Fb on A. Since force is the rate of change of momentum, it logically follows that throughout their interaction, the rate of change of momentum of object A is exactly opposite to the rate of change of momentum of object B. This leads us directly to momentum conservation. The core idea is illustrated on slide 34. If no external force acts on a system, the total momentum of the system is a conserved quantity. In a head-on collision of two balls, for instance, we consider the two balls together as our system. The forces they exert on each other during the collision are internal forces. If we assume no external forces, like friction from the table or air resistance, are significant, then the net external force on this system is zero. Therefore, the momentum before the collision equals the momentum after the collision. MAVA plus MBVB equals MAVA prime plus MBVB prime, where the prime symbol indicates the velocity after the collision. On slide 35, we see that our derivation of the conservation of momentum can be extended to include any number of interacting objects. If we have a system of n interacting objects, the total momentum p is simply the vector sum of the individual momenta of all the objects. P equals m1v1 plus m2v2 plus ... mnvn equals sigma pi. Now, let's differentiate this total momentum with respect to time, as shown on slide 36. If p equals sigma pi, then dp dt equals sigma dpi dt. And since we know from Newton's second law that dpi dt is equal to the net force acting on the ith object, Fi, dp dt equals sigma Fi. Here, Fi represents the net force on the ith object. On slide 37, the forces acting on objects within our system can be categorized into two types. Internal forces. These are forces that objects within the system exert on other objects within the system. External forces. These are forces exerted on objects of the system by objects outside the system. As slide 38 explains, by Newton's third law, internal forces always occur in pairs of equal magnitude and opposite direction. This means that all the internal forces within a system cancel each other out in pairs. Therefore, any change in the total momentum of the system can only occur as a result of external forces. Internal forces only redistribute momentum within the system. They cannot change the system's total momentum. So if we put it all together, as on slide 39, the rate of change of the total momentum of a system, dp dt, is equal to the sum of all external forces acting on the system. dp dt equals sigma F external. This is the very powerful law of conservation of momentum. When the net external force on a system of objects is zero, the total momentum of the system remains constant. Mathematically, if sigma F external equals 0, then dP dt equals 0, which implies that P equals constant. We can also state the law of conservation of momentum more simply, as on slide 40. The total momentum of an isolated system of objects remains constant. An isolated system means one where no external forces act on it. The only forces present are internal forces, those between objects within the system itself. What happens if there is a net external force acting on a system? Slide 41 addresses this. If a net external force acts on a system, then the law of conservation of momentum in its strict form would not apply to that specific system. However, often we can redefine the system to include the objects that are exerting those external forces. By doing so, those forces become internal forces within the new, larger system, and then the conservation of momentum principle can be applied. Let's look at an example. On slide 42, let's use the example of a rubber ball dropped towards Earth. Initially, if our system is just the ball, then gravity from Earth is an external force, and the ball's momentum is not conserved. It increases downward. But what if we redefine our system to be the ball plus Earth? Now, the gravitational forces between the ball and Earth are internal interactions within this new, larger system. Since there are no other significant external forces acting on the ball-Earth system, this is an isolated system. Therefore, for the ball plus Earth system, the total momentum is conserved. P equals P ball plus P Earth equals constant. This means as the ball falls and gains downward momentum, the Earth gains an equal amount of upward momentum. Though due to its immense mass, the Earth's change in velocity is infinitesimally small and unnoticeable. The law of conservation of momentum is particularly useful, as seen with rocket propulsion on slide 43. For example, rocket propulsion can be understood on the basis of action and reaction, Newton's third law, and can also be explained on the basis of the conservation of momentum. We can consider the rocket and its fuel as an isolated system while it's far out in space, where external forces like gravity and air resistance are negligible. This figure on slide 44 illustrates the rocket propulsion in more detail. Before the fuel is ignited, the rocket and fuel system is at rest, meaning its total momentum is 0. P total equals 0. When the fuel burns and gases are ejected backward, these gases gain significant backward momentum, Pg. To conserve the total momentum, keep it 0, the rocket itself gains an equal and opposite forward momentum, Pr. So P total equals Pr plus Pg equals 0. The total momentum of the rocket gas system remains 0. This is a powerful demonstration of momentum conservation. Now, let's recap on slide 45, summarizing what we've covered so far. We've established that the rate of change of an object's momentum is equal to the net force applied to it, sigma F equals dP dt. We also saw that forces between interacting objects are equal and opposite, leading to the conservation of total momentum in an isolated system. If, however, we manipulate the above equation into the following, integral f dt equals delta p, we see that each object's change in momentum depends on the force as well as the length of time the force acts on each object. This quantity is called impulse. Let's study it in more detail. This leads us to our final topic, impulse, which you'll find on slide 46. On slide 47, we start by looking at what happens during a collision. During a collision between two ordinary objects, their molecular bonds act somewhat like tiny springs. As the objects collide, these bonds compress and deform. If the materials of the objects are different, the amount of compression or deformation for each object will also be different. But a key point, according to Newton's third law, the force that each object exerts on the other during the collision will be equal in magnitude and opposite in direction. But if they have different masses, their accelerations will be different. Moving to slide 48, we define impulse. As we just saw, if we rearrange Newton's second law, F equals delta P over delta T, we get F delta T equals delta P. This quantity, impulse, I, is defined as the product of the average force, F, acting on an object, and the time interval over which it acts. Impulse, I, equals F delta T. And importantly, impulse is equal to the change in momentum, delta P. I equals delta P equals P final minus P initial equals delta mv equals m delta v. So a larger impulse means a larger change in momentum. On slide 49, this has a very practical consequence. For a given change in velocity, and thus a given change in momentum of a fixed mass, let's say a person in a car, the force experienced is inversely proportional to the amount of time it takes for that change to occur. F proportional to 1 over delta t. This means the longer it takes to change momentum, the less force is applied or experienced. The shorter the time, the more force. Look at the graph. A very short time interval means a very large force peak. A longer time interval means a smaller, more spread out force. This principle is vital in safety engineering.
On slide 50, in a real collision, the force isn't constant. It usually jumps from 0 at the moment of contact, rises to a very large peak value during maximum compression, and then quickly returns to 0 as the objects separate or deform permanently. The graph shows this typical force time curve with distinct compression and expansion phases. The area under this curve is the impulse. This inverse relationship is why modern cars, as shown on slide 51, are designed with crumple zones. You can see these designated areas at the front and rear of the car, as well as the passenger safety cage and airbags. These are all force-reducing measures. On slide 52, we see a real example of a car designed with these zones. Here, we see a car that has been intentionally cut to show its internal structure. The yellow metal here represents a crumple zone, and it is intentionally weaker or more deformable than the red metal, which forms the strong passenger cage. Let's explore the yellow metal on slide 53. Think of the atoms of the metal as being like springs. When a car hits a wall, the yellow metal springs in the crumple zone are designed to be more easily compressed. This means they have a smaller spring constant, K. By compressing more, these parts of the car take a longer time to deform and bring the car to a stop. This significantly lessens the average impact force experienced by the occupants, as per our impulse equation. F equals delta P over delta T, or F is proportional to 1 over delta T. This deformation also absorbs a lot of the kinetic energy of the collision, turning it into deformation energy and heat, preventing that energy from reaching the passengers. Finally, on slide 54, let's consider the red metal. On the other hand, the red metal, which forms the passenger safety cage, is designed to be much stiffer. These springs have a higher spring constant K. They are designed not to compress much. This is a good thing. You do not want the passenger compartment to crumple, as this would directly expose the occupants to severe forces. The goal is to keep the passenger space intact while the crumple zones absorb the impact. And that brings us to the end of our lecture on energy and momentum. We started with Hooke's law, understanding how springs store elastic potential energy. We then explored the basic energy model, recognizing that energy is conserved within isolated systems, transforming between kinetic, potential, and thermal forms. We learned the distinction between conservative and non-conservative forces, with friction being a prime example of the latter, always increasing thermal energy. We defined power as the rate of energy transfer. Then we delved into momentum, understanding it as a vector quantity central to Newton's second law and the powerful conservation of momentum principle in isolated systems. Finally, we looked at impulse and its crucial application in real-world safety features like car crumple zones, where extending the impact time significantly reduces the force experienced. These concepts are fundamental to physics and have wide-ranging applications in engineering and everyday life. I hope this lecture has provided you with a clear understanding of these essential topics. Thank you for your attention. Are there any questions?